Okay, so remember, we're talking about constraint satisfaction problems. So we've talked about two different kinds of problems so far, and it's really important to keep them straight. We cover a lot of stuff in this class because AI is a huge field, but you guys are mostly seniors and you're grown-ups and you can take it. So we're just going to keep blasting through the material. Shortest path problems, you don't know how many steps there are to go. Like the tree could be infinite. We don't know how long the plan is going to be, so we want a least cost path to a goal. So this kind of a problem is sort of, you see this kind of problem, you think A star, something like that, maybe beam search if we're going to run out of memory.
Could you combine A star and beam search? Is that
Well, I mean, beam search is already using F, right? I mean, how do I adjudicate which of my kids go on the chopping block? It's all F. That's what you. So in that sense, the secret sauce of A star, that H function, it's in there. You've already added it to the mix. Yes, you can, and we did. Yes. Constraint satisfaction. Whoa.
For problems with a perfect heuristic available to them, are those actually?
Why are you talking fantasy talk to me?
Because they do exist, but like you know the depth, you know the
Because of F or H, yeah.
If you know the initial F, then you know how long it's going to take.
Yeah.
Does that count as shortest path still, or is it a different type of problem?
So if what someone is giving me is the cost to go, I'm totally going to run A star. Because CSP kind of algorithms, like depth first search, well, I don't know, actually. That might be an interesting boundary case. Well, you know what I'm really going to do? If you give me a perfect heuristic, I'm going to run hill climbing. Hill climbing is an algorithm we're going to talk about here, but since you asked. Hill climbing, yeah. I'm here at the initial state. I generate my kids. I evaluate the heuristic. And I choose the kid with the best F. I forget about everything else. I even forget my parent. Just totally me focused, like the 80s. It's like the me decade. We just moved to that, I want to be that best kid. Great. Generate my kids. Find the best one. Go. Every step, best move. Go, 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 go. Right on, I hope, to the goal. If my heuristic is lousy, this is a recipe for disaster. If my heuristic is perfect, it's a recipe for getting to the solution very quickly with no memory. So that's what I'm going to do if you give me the perfect heuristic. Now, the question of which of these is more appropriate is that's a beefy question. And if you want me to answer it in more detail, ask it as an end of lecture question. Usually, a depth first sort of a search, people often don't order the children on cost, or at least not on F. If some very fancy people order their kids on H. Anyway, so here we have unknown depth, least cost path. Here we have fixed depth because we already know the choices. Someone's laid it out in front of us. Like map coloring. We have this sequence of decisions need to be made. So this is a very important distinction. Okay, heuristics. The motivation for choosing the most constrained variable. Adam.
Cuts down most of the tree initially.
Why?
You're only dealing with a small domain, and eliminate part of that.
I got two variables to choose. One of them has a small number of values in its domain. One of them has a large number of values in the domain. You're telling me I should choose the most constrained variable that has the fewer number of values. And I'm sorry, why do I choose the one with fewer number of values in its domain?
To eliminate those,
It has something to do with keeping the tree small. Frank?
Those overbranching factor.
Yeah, the size of a tree is usually like b to the d, and if we lower b, then b to the d is smaller. Okay, value choice. Value choice. And so this is a great thing to do. This variable choice heuristic of the most constrained variable is a great thing to do when you're using forward checking, because forward checking is pruning down your domains as you go. So a lot of times with like a coloring problem, for example, in the beginning everything has the same size of domain. And if you don't do forward checking, every variable is constrained to the same amount, and it's not very exciting. But if you're doing forward checking, then you end up with variables having different domain sizes, and this becomes a very effective heuristic. For value choice, which branch do I go down first? How do I order my children in the tree? I said last time to try the least constraining value first, the one that causes the fewest removals when we do forward checking. And what's the intuition behind that recommendation, behind that heuristic? Anybody have a recollection? Tyler.
Well, I would say that, the more domain, like pieces that you eliminate higher up in the tree, the less chance you're going to get to a final solution.
Yeah, and why would we want to not do that first? I mean, I have a bunch of values here, and I've chosen a variable. I have a bunch of values for it. I want to try the least constraining value first. Why?
Because I would say it has a higher success chance.
Yeah. Why do I want to try the highest success chance first?
To avoid space and time wasting.
Why does it help me avoid time wasting? Space we don't care about because we're doing depth first search. So we got all the space and we're just doing linear space. It doesn't really matter. But time is key. Mortality's upon us. Joe, were you raising your hand?
Yeah, I could feel like less chance of domain like that, backtrack.
What's wrong with backtracking? Yeah. So, yeah. If you can succeed, you might as well do it fast. If the problem is unsolvable, it doesn't matter what order you do them in. And if the problem is solvable, you might as well solve it soon. So we choose the one that has the highest success probability. Just like Tyler was saying, if it doesn't remove a lot of other values from the other variables' domains, it's leaving more possibilities open for the future. And more possibilities is good. This is why we're going to college, right? You have more possibilities in the future.